New class, I'm glad to be back, and I hope you are too. I hope you had a blessed Easter and really enjoyed the time and got close to Christ. Our pastor on Saturday night said now all we have to do is stay close to Christ the rest of the year. So let's see if we can work on that. Here we are on Tuesday, March 14th, and we're on section 13.3, Compound Events in your book on page 572. So this is continuing on with probability. So here we have example 1. An experiment consists of flipping a coin followed by rolling a number cube, just a regular number like in Yahtzee, cube in Yahtzee. So let event A be the results of heads on the coin and event B be the number 2 on the number cube. So A, are the two events independent or dependent? Well, clearly they're independent because the coin you're tossing and the cube you're rolling don't have any connection whatsoever. Now, next, B is state the sample space, which is to state every possibility that could happen. Well, how many things could happen? You could have 6 rolls on the dice times 2 flips of the coin. So 2 times 6 is 12, and this is just us listing out the 12. 6 with the heads and 6 with the tails. So we can list it as H1, H2, H3, H4, H5, H6, where H is heads, followed by T1, T2, T3, T4, T5, T6, where tails is first and then the number. Now for part C, find A equals the probability of heads, which is 6 over 12 or 1/2, and find probability of B, which is the probability of rolling a 2, which is 2 over 12 simplified to 1/6. Now, as it said in the section we're in, compound events, this is a compound event. Part C, find probability of A and B occurring. So when they're independent from each other, you can multiply the probabilities as we're doing here. Probability A times probability B is 1/2 times 1/6 or 1/12 of both the heads and a 2 being rolled. Now, this is just stated generally now is if events A and B are independent, then probability of A and B is above probability of A times probability of B, as we just did in our example. Now for example 2, and this I've seen these on the ACT tests, a bag contains 6 white balls, 3 red balls, and 1 purple ball. Find the probability of drawing a white ball, then replace the ball, and then drawing a red ball from the bag. So you pick one out, the chance of it being red, put it back in, and then draw another one. This is called with replacement, means there are always 10 bags still in the ball. They never get any less. So the probability of picking a white followed by a red, which we call PW1 and R2, is PW1 times PR2, since the colors are certainly separate, which would be 6 over 10 white balls times 3 over 10 red balls, is 18 over 100 equals 0.18 or 18%. Now for dependent events, without replacing the thing that you draw each time, gives you 1 less total ball each pick. So doing it that way, probability of picking a white first and then a red is probability of white 1 times probability of red 2. Then the slash W1 means given that W1's already occurred. And all that means is that there's 1 less ball in the bag. So we have 6 over 10 times 3 over 9, that's the without replacement. So that gives us 18 over 90, which is 0.2 or 20%. Notice a little higher than the 18% when there was with replacement, where there was always 10 balls. So then for general case, we can say the probability of dependent events, if A and B are dependent, like if they pick one and there's 1 less each time, then probability of A and B is probability of A times probability of B, given that A has already occurred, or say something has already been picked. Now in example 3, we still have a bag contains 6 white balls, 3 red balls, and 1 purple ball. Find the probability of each event if the first draw is not replaced, so we lose one each time. So A, probability red then white, we just did that. 3 over 10 would be the red chance, and 6 over 9 would be the white chance, given that one's already been picked to make the denominator 9. That would become 18 over 90, or 0.2 again, which is 20%. Now let's look at the probability of drawing 2 red balls, which is 3 over 10 times 2, because there's 1 less red ball, over 9, because there's 1 less ball total. So that comes out to 6 over 90, which is equal to 0.067, or roughly 7%. Okay, now this table is called the contingency table, where we're looking at brown eyes and male and female. So this looks down on the first column down where it says brown eyes. There's 5 females with brown eyes, 6 males with brown eyes, so there's 11 total with brown eyes. Now in the next column over, there's 3 females that don't have brown eyes, 4 males that don't have brown eyes, so 7 total don't have brown eyes, and the totals over here are 8 males with brown eyes, 10, or males and females, 10 males and females that are not brown eyes, or no, excuse me, the 8 over here is 8 males, and this is 10 females with a total of 18 people in the trial. So now, experiment 4 using this table is find the probability of brown-eyed male. Now to be a brown-eyed male, there would be in the first column 6 out of 18 total. So remember, the 6 is where the brown eyes and the male intersect. So the first column, second row is 6. So this is 6 over 18, or 1 over 3. Now, check to determine whatever brown eyes and male are. And so for the next one, we see with independence that what's the probability of male and brown eyes is the probability of male times the probability of brown eyes, which is 10 over 18. Notice 10 on the second row across, 10 males, and then there's 11 brown eyes. So 10 over 18 times 11 over 18, which is 55 over 162, or 1/3. And when we look at it being dependent, which it usually more likely is, we have the probability of male and brown eyes as probability of male, which still stays 10 over 18 because there's 10 males, times the probability of brown eye given that it was a male, which makes it now 6 over 10. And what we can do there is, we can cross out the 10 over 18 and the 6 over 10. The 10's cross out on the diagonal, so we're left with 6 over 18, which is 1/3 again. Okay, so for the probability of A or B now, this is different than AND, where they both happen at the same time or in sequence. This is the probability of A or B. So in general, the probability of A or B is the probability of A plus the probability of B minus the probability of A and B where they overlap. And that's called inclusive, an inclusive event. Now, if A and B don't have anything to do with each other, then probability of A or B is probability of A plus probability of B, which is called exclusive or mutually exclusive. It's easier seen as an overlap, though. So now in example 5, probability of female or brown is probability of female plus probability of brown, which is 8 over 18 plus brown is 11 over 18, and the brown-eyed females, The and is 5 over 18 because 5 females are brown-eyed in the top row, first column. So we have, let me see, it's hard to see that. 8 plus 11 minus 5 is 14 over 18, or 7 over 9, which is 78%. Okay? So you see that it's the probability of all female plus the probability of brown, which is the female is the top row across, that's 8. The probability of brown is 11, see? So down here we had the probability of female is 8 over 18 plus the probability of brown is 11 over 18 minus the probability of female and brown is 5 over 18, and that's what we subtract, which came from the top row first column of 5 females that have brown eyes. Okay? So that's example 5. Now example 6 is rolling 2 dice like you would the dice from Yahtzee, but just 2 of them. So how many possibilities are there? 6 possibilities for the first dice and 6 for the second. So altogether, there's 6 times 6, or 36. So example 6 wants to know, when a pair of number cubes is rolled, what is the probability of getting a sum less than 4 or greater than 9. Okay? So now, these events are mutually exclusive because getting a sum of 4 less than 4 or a sum greater than 9 can't happen at the same time. That's what mutually exclusive means. So what are the possibilities of a sum less than 4? Well, here I've indicated getting a 1 plus 1, a 1 plus 2, or a 2 plus 1, accounting for the different dice, would be 3 over 36. Okay, because there's 36 possible combinations. And probability of getting a sum greater than 9, going in order, would be 4 plus 6, 5 plus 5, 5 plus 6, 6 plus 4, 6 plus 5, 6 plus 6, or 6 different ways out of 36, or 1 over 6. So the probability, now putting them together, of getting a less than 4 or a greater than 9 sum, they are mutually exclusive, so we can add the individual probabilities with no overlap of 3 over 36 plus 6 over 36, which is 9 over 36, or 1 over 4, which is 25%. Okay, now here's the homework, which starts on page 575. And now it says classify the events as inclusive, which means there's an overlap, or mutually exclusive, which means they have nothing in common. So part A, rolling a 3 or rolling a 5 on a number cube, they have nothing to do with each other, so they're mutually exclusive. But buying a hammer or buying nails at the hardware store, if you bought one, you most likely bought the other, so those would tend to be dependent or inclusive. Now C, being a junior or being on the varsity team, you could be a junior on the varsity team, so that has some overlap, that makes it inclusive. And getting an A or a B on the final is, in a biology class, we can't have both an A or a B at the same time, so those have nothing in common or mutually exclusive. So now on 4, problem 4, it says drawing out marbles from a bag containing 7 red, 4 blue, and 3 orange marbles. Okay, if probability of blue or red is the probability of blue plus the probability of red, because they are mutually exclusive, so there's 7 reds out of 14 plus 4 blue out of 14, making 11 out of 14 is our answer, just adding them. Now for problem 6, we have a contingency table like we had for the males and females with brown eyes. Now we're looking at boys and girls in a class that are both left-handed or right-handed, but not both, of course. We're not looking at ambidextrous. So for left-handed, we have 2 boys that are, 3 girls that are, total 5 that are. Second column, More people are right-handed, if you've noticed. 7 boys that are right-handed, 5 girls that are right-handed, and 12 total that are right-handed. Now, adding our columns across to the side, we have 9 boys, 2 plus 7, and 8 girls, 3 plus 5, and a total of 5 plus 12 or 17 people involved. Now, the probability of right-handed girls, which we're asked for here, is the one I have circled, the 5, which is in the second row, girls, and the second column, right-handed. So that would be 5 over 17. Now, problem 8 is the probability of a boy or a righty, which would be the probability of boy plus the probability of a righty minus the probability of a boy and a righty. Now, the probability of being a boy, as we saw from our table, was 9 over 17, but the probability of being right-handed was 12 over 17, and the number of boys that are right-handed is 7 over 17, and that's what we would subtract. So 9 plus 12 is 21, minus 7 is 14 over 17, for our inclusive event that has overlap of boys and right-handed, okay? So 10 is probability of A or B now, different one. If probability of A equals 0.34, probability of B equals 0.12, and A and B are mutually exclusive, which allows us to add them separately. So probability of A or B is probability of A plus probability of B, which is 0.34 plus 0.12, which is 0.46. Now 12 is probability of A or B if probability of A equals 0.48, probability of B equals 0.25, and probability of A and B, the overlap, is 0.17. So now probability of A or B is equal to probability of A plus the probability of B minus the probability of A and B, which is 0.48 plus 0.25 minus 0.17, or a final answer of 0.56. Now for 14, what's the probability of B given A? We haven't done like this before. If probability of A and B equals 0.21 and probability of A equals 0.7. Now the way that we have to determine this is to use the rule for dependent events, which is the probability of A times the probability of B given A, which is what we're trying to find, equals the probability of A and B. And so now dividing both sides by probability of A, we're left with probability of B given A equals the probability of A and B over the probability of A, which is 0.74 over 0.21, giving us the final answer of 0.28.